Hello dear students, I'm Assistant of Azerbaijan Medical University, Faculty of Pharmacy, Department of General and Toxicological Chemistry, Əkbərova Səidə. Today we begin the second lecture on analytical chemistry. The name of the lecture second lecture is Protolitic theory of acids and bases. The acidic and basic properties of substances have a decisive significance for the course of almost all analytical reactions. Acidity and basicity are the most important characteristics of substances. Knowledge of these properties, the ability to calculate and apply them for the purposes of analysis, is the main part of the functional activity of an analytical chemist. Classical ideas about acids and bases are based on the theory of electrolytic dissociation, developed by Swedish chemist Arrhenius. According to this theory, the acids that are released during the dissociation of the oxonium ion or hydroxonium belong to acids, to the bases hydroxide ion, ions released during the ionization of water. Look at the dissociation reaction of the water molecule. Water is dissociated on positively charged hydrogen and negatively charged hydroxide group. Or in case of the dissociation of the strong acid of hydrogen chloride, it's dissociated on positively charged hydrogen proton and negatively chloride ion. Bases, strong bases, for example, sodium hydroxide, by dissociation is formed sodium positive and hydroxide ion. The theory of electrolytic dissociation does not explain the acidic or basic properties of organic compounds. For example, amines, amides. It's also unclear what substances are considered acids and bases in non-aqueous solvents. Theory of Arrhenius, theory of electrolytic dissociation. Arrhenius defined as acid as a substance that liberates hydrogen ions, and a base as a substance that supplies hydroxyl ions on the dissociation in aqueous media. According to the Arrhenius theory, acidic solutions contains hydrogen proton, and alkaline solution contain hydroxide groups, alkalis or water-soluble bases. The theory of electrolytic dissociation has several disadvantages. This theory cannot explain the true cause of the dissociation process. The theory of electrolytic dissociation does not explain the acidic or basic properties of organic compounds. For example, amines, amides. It's also unclear which substances are considered acids and bases in non-aqueous solvents. Does not take into account the role of the solvent in the regard. Does not assess the possibility of ion solvation in solution. A more general theory of acids and bases explaining the facts listed above was created by the Danish chemist Bronsted and stimulously with the English chemist Lowry in 1923. The protolytic theory considers acids and bases in protic solvents. These are solvents that themselves can both donate and bind a proton. The most important solvent of this type is water. Other substances include alcohols, ammonia, and some organic acids. Acids and bases are defined by the role of particles in proton transfer. Protolytic theory of Bronsted and Lowry. According to its theory, acids, the donors of protons, bases, acceptors of protons. As a result of the recoil and adoption of protons, acids and bases form conjugate acid-base pairs. An acid is a particle that reacts like a proton donor. In addition to ordinary molecular acids, this concept covers any ions that can donate a proton. One of the simplest ions of this type is ammonium. Ammonium is a part of salts, and therefore ammonium salts and some of other salts can be considered as acids. A base is a particle that reacts as a proton acceptor. Obviously, metal hydroxides are bases because the hydroxide ion present in them binds a proton, turning into a water molecule, but this definition is much broader, since in salts all anions of weak acids can bind protons, turning into acid molecules. Therefore, the bases are not only metal hydroxides, but only salts. There are also many molecular substances, mainly organic, capable of attaching a proton. Theory is called the protolytic theory of acids and bases, since it is based on the ratio of substances to protons, hydrogen ions. The protolytic theory of acids and bases refers to acids of a substance that release protons during ionization. To the bases are substances that attach protons. In this case, in the reaction, hydroxonium ion in this case is acid because it's released proton, but hydroxide ion is base which attach proton. Protolytic theory also introduces the concept of conjugated acids and bases. For example, hydrogen cyanide acid releases a proton and forms a conjugated base, cyanide ion. In an acidic environment, the base, conjugated base, cyanide ion can attach a proton and form a conjugated acid, hydrogen cyanide, with it. Many substances are capable of both addition and release of protons. For example, the hydrogen carbonate anion in an alkali medium allocates a proton and behaves like an acid in other conditions in an acidic medium. The proton but in other conditions in an acidic medium the proton attaches exhibiting the properties of the bases. We can see it from the reaction of the interaction. Sodium hydrocarbonate with acids, in this case hydrocarbonate, it's attach hydrogen. In another reaction, it's allocated proton. In different amphalites, many dominate both acidic and basis properties. It was noted above that sodium bicarbonate creates a weak alkaline environment in the solution. This substance has basic properties. Such substances are called amphoteric compounds or amphalites. The interaction of acids and bases can be represented as half reactions combined into one acid-base reaction of proton redistribution between acids and bases. It shows in two half reactions. In the first reaction, recomposition of the first acid into conjugated base and hydrogen proton. In the second one, the composition of the base on attach hydrogen proton and form conjugated acid, and the combined form the reaction between acids and bases. A protolytic reaction is the reaction of a proton transferred from an acid as donor to a base as a proton acceptor. Denoting the acid as hydrogen B1 and the base B2, we write the protolytic reaction in the general form. The initial acid, hydrogen B1, having given up a proton, is converted in the conjugated base B1- negative, and the initial base B2 by adding a proton is converted into the conjugated acid hydrogen B2 positive. Protolytic reactions are reversible. Both products on the right side of the equation react with each other in a reverse reaction. The equilibrium of the protolytic reaction shifts towards the formation of the weaker acids and bases from the particles participating in the reaction. For example, it's a reaction between hydrocarbonate ion with the attached hydroxide ion with the bases. In this case, carbonate ion is released. The charge of the conjugated base is always one more negative than the charge of the acid. For example, the reaction is the reaction of a strong acid with water form the conjugated acid and conjugated base. Here, hydroxide ion as acid, conjugated acid with an initial base water, and chloride ion, it's a conjugated base, is with an initial acid hydroxide ion. The charge of the chloride ion conjugated base is one more negative than the charge of the hydrogen acid, hydrogen chloride acid. Reactions accompanied by the transfer of protons are called protolytic, and the equilibrium state arising during their passage is a protolytic equilibrium. An important place in the protolytic theory is protolysis of solvents. For example, water protolyzes by the next equation, two water molecules protolyzes on conjugated acid hydroxonium ion and conjugated base hydroxide ion. In this case, one molecule of water acts as an acid, separating the proton. The other molecule of water, the base, which is taken it, in this case a new acid, conjugated acid, hydroxonium, and a new base, hydroxide ion, are formed. Or another example, what conjugated pairs are involved in the reaction of acetic acid with ammonia? Let's write a protolytic reaction of the weak acid with ammonia. In this case, the reaction involves conjugated pairs, acetic acid and acetic ion, another pair, ammonium and ammonium positive ion. Both particles on the left side of the equation, acetic acid and ammonia, correspond to the weaker conjugated base. An acid on the right side of the equation. The equilibrium of this reaction is shifts to the right. A great contribution to the development of protolytic theory was made by the Soviet scientist Izmailov, who justified protolytic equilibrium in non-aqueous solutions. Non-aqueous solvents, like water, protolyze to a solvated proton and anion. For example, methanol protolyzes to cation and anion. In this reaction, this positively solvated cation is lion, it's as acid, and this solvated anion or light is base, conjugated base. In another reaction, in the protolytic reaction of the ammonia, two ammonia molecules protolyzes on solvated cation lion, NH4 positive, it's as conjugated acid, and another ion is solvated anion, it's liat, which is the conjugated base. One of these molecules behaves like acid, another like base. Upon dissolution of acid and base in a solvent, a protolytic reaction occurs between them and solvent molecules. Acids and base in a solvent, we can see the protolytic reaction which is occurs between them. In this case, form conjugated acid and conjugated base, or in the reaction, protolytic reaction of acetic acid, from the two acetic acid molecules form one conjugated acid and one conjugated base. However, the protolytic theory doesn't explain the acid-base properties of compounds that don't interact with protons. For example, liquid sulfur dioxide undergoes the self-ionization, although protons don't participate in the reaction. The best known theory of Lewis and Usanovich According to the theory of Lewis, acids are compounds capable of taking a pair of electrons with the formation of a covalent bond. The bases are compounds capable of providing a pair of electrons for the formation of covalent bond. The compounds corresponding to the provisions of this theory are called Lewis acid and bases. For example, the Lewis acid is hydrogen ion. The base is ammonia in the interaction of ammonia with a hydrogen proton. In this case, ammonia gives up an electron pair. It's a base. Another proton, hydrogen proton, accepting an electron pair is an acid. Forms an ammonium ion with a covalent bond. According to the electronic theory, very many types of chemical reactions belong to the acid-base reactions, up to complexation and oxidation reduction. These too much exposition of the concepts of acids and bases is one of the weaknesses of Lewis theory. A generalized idea of acids and bases is given by the theory of Soviet scientist Usanovich. According to Usanovich, acids allocate cations and interact with anions or electrons. Bases give out anions or electrons that combine with cations. The acids and bases react with the formation of salts. For example, the interaction between sulfur dichloride and sodium sulfate in liquid sulfur dioxide is an acid-base reaction. Sulfur dichloride is an acid releasing the sulfur oxide 2 positive cation, and sodium sulfate is the base that releases sulfate anion. The interaction between the cation and anion takes place with the formation of the solvent molecules. According to the Usanovich's acids and bases, acids could be either of the following: a substance that donated a cation, a substance that accepted an anion. According to the Usanovich theory, bases could be either of the following: a substance that donated an anion, a substance that accepted a cation. According to the Usanovich's theory, oxidation-reduction reactions also apply to acid-base reactions. For example, in acid-base oxidation reaction, for example, between iron salt and tin bivalent salt, in this case iron 3 positive is acid, tin 2 positive is base. Many methods of chemical analysis involve the detection and determination of acids and bases. According to the Protolitic theory, acids include 3 types of substances: neutral acids with the general formula hydrogen A. There is hydrogen chloride, nitric acid, acetic acid. By their protolytic reaction, form positively charged proton and anion chloride. Cationic acids with a general formula BH positive, there is ammonium, hydroxonium ions. It's a decomposition protolytic reaction of ammonium into ammonia gas and hydrogen positive, and ionic acids with a general formula hydrogen A negative, there is a hydrogen sulfate, dihydrogen phosphate ions. For example, the composition of dihydrogen phosphate ions form hydrogen proton and hydrogen phosphate anion. Each of these acids is capable of donating proton. Ionic product of solubility. Water molecules are highly prone to hydrogen bonding. So in water there are associates of several molecules called clusters. The thermal motion of molecules inside a cluster can weaken the hydroxide bond or H bond in one of them and break it. With such a break, a proton is attached to a water molecule due to the conversion of the hydrogen bond into a donor-acceptor one. Under certain conditions, water can act as a proton acceptor in the presence of an acid, or as proton donor in the presence of base. An interesting feature of water is that it can undergo a process of self-dissociation or auto-ionization, or be both a donor and an acceptor of protons in relation to itself. In this case, the oxonium ion and hydroxide ion formed. In a simplified form, we can write the protolytic reaction of water in this following form: decomposition of water on hydrogen and hydroxide ions. Such processes are called processes of self-ionization or autoprotolization. The water self-protolization is described by the equilibrium constant, the value of which 1.8 multiplied 10 to the minus 16 power was determined experimentally. This value was determined experimentally, and taking the concentration of water in the system for a constant value for 55.55 mole liter, we obtain an autoprotolization constant or ionic product of water. And the reaction is take place in the form constant, equilibrium constant equal 1.8 multiplied 10 to the minus 16 power. Hence, the product of constant values of a constant of water autoprotolization equal to the 10 to the minus 14. The concentration of water is usually included from this expression due its almost constant value in dilute solutions. We get a new equilibrium constant, which is called ionic product of water. In this case, it's equal concentration of hydrogen multiplied to the concentration of hydroxide ions. At a temperature of 25 Celsius degree, water protolization equal 1.1 multiplied 10 to the minus 14 power and remains constant in aqueous solutions of acids, alkalis, salts, or other compounds. And its constant is equal 10 to the minus 14 power. And with increasing the temperature, ionic product of water is greatly increased. The resulting expression is applicable not only to pure water, but also to solutions if the condition of concentration of hydrogen equal to the concentration of hydroxide ions is fulfilled, and then the solution is called neutral. But usually these values don't coincide. Then with an increase in one indicator, the other should decrease so that their product remains constant. During autoprotolysis, one hydrogen ion and one hydroxide ion are formed from a water molecule. In the absence of foreign compounds in the water, therefore, their concentrations are equal to each other. For convenience, the autoprotolysis constant is represented as an index of water autoprotolysis constant, which is the inverse logarithm of the autoprotolysis constant. It's equal 14. Acidic-basic properties of solutions are determined by the concentration of hydrogen or hydroxyl ions. We already know that the ionic product of water at a certain temperature is constant, and concentration of hydrogen and concentration of hydroxide ions are variable. Then by their values we can talk about the acidity or alkalinity of the solution. In 1 liter of pure water, the concentration is constant and equal 55. Concentration of water is equal 55.55 mole liter. That is at 22 Celsius degree. In 1 liter of water contains 55.55 mole of water. If we write this expression in the equation, we get the ionic product of water, or the constant of autoprotolization, and it takes place in the form the product of the concentrations of hydrogen and hydroxide ions equal to the constant of autoprotolization, and it's equal 10 to the minus 14 power. With autoprotolysis, from the water molecule, one hydrogen ion and one hydroxide ion are formed, and their concentrations are equal, and it's equal to the 10 to the minus 7 power. The concentration of hydrogen and hydroxide ions by Sorensen in 1909 was suggested to be decided in the form of hydrogen and hydroxide index, the inverse logarithm of the concentration of hydrogen and inverse logarithm of hydroxide ions. For example, in the case of calculation pH, its inverse logarithm of the concentration of hydrogen. In case of the POH, inverse logarithm of the concentration of hydroxide ion. And from this, the index of the autoprotolization it's equal pH plus POH, it's equal 14. The sum of hydrogen and hydroxide values in water is constant and equal to the index of autoprotolysis constant. The addition of acids and bases to water causes shifts in the equilibrium of the autoprotolysis reaction due to the appearance of an excess of one of these ions, hydrogen or hydroxide. For example, in 0.1 molarity concentration of hydrogen chloride, the concentration of hydrogen ion is equal to the concentration of acid, hydrogen chloride acid. So, if the concentration of hydrogen chloride acid is 0.1 mole, so the concentration of the hydrogen ion equal 10 to the minus 1 power, and pH is 1. So calculate pH for 0.1 mole for hydrogen chloride solution. Since index of constant of autoprotolysis is a constant value with an excess of hydrogen ions, the process of water ionization decreases, the equilibrium shifts towards the formation of water molecules. The concentration of hydroxide ions decreases, it becomes equal to, if pH equal 1 and the sum of pH and POH is 14, so from this it is found POH is equal 13 and concentration of hydrogen ions it is equal to the concentration of acid, so 0.1 or 10 to the minus 1 power, and the concentration of hydroxide ions equal 10 to the minus 13 power. Similar phenomena occur when an excess of alkali is added to the water. For example, in 0.1 molarity concentration sodium hydroxide alkali, concentration of hydroxide ions is equal to the concentration of the base 10 to the minus 1. From this, POH equal 1, pH equal 13, so concentration of the hydrogen ions equal 10 to the minus 13 power. An increase or decrease in the concentration of hydrogen ion or hydroxide ion changes the nature of the environment. Thus, in solutions with different characters of the medium at a temperature of 25 Celsius degree, the following conditions are satisfied. In acidic solutions, concentration of hydrogen ions more than 10 to the minus 7 and pH less than 7. The medium is considered acidic. In base solutions, concentration of hydrogen ions less than 10 to the minus 7 power, so pH more than 7, the medium is considered alkaline. At pH equals 7, the medium is considered neutral. Therefore, at pH less than 7, the medium is considered acidic, At pH more 7, alkaline. At pH equals 7 is neutral. It should be remembered that regardless of the nature of the medium, both ions always exist in aqueous solutions. Expressing the nature of the medium in this way is informative, but it is fraught with some difficulties in the case of expressing small values of the concentration of the hydrogen ion. It is more convenient to use the negative logarithm of this quantity called hydrogen ion exponent, which is equal to inverse logarithm of concentration of hydrogen ion. The values of the hydrogen and hydroxide index form the basis of the scales of the acidity and basicity of solutions, or the scale of pH and pOH. The following figures show the dependence of the nature of the medium on the pH value. As we see, by increasing of acidity, the concentration of hydrogen ions is increased, and by increasing of basicity, the concentration of the hydrogen ions is decreased. So, by increasing of acidity, pH values is decreased, and by increasing of basicity, the pH value is increased. Or by increasing of acidity, value of pOH is decreased, concentration of hydroxide ions is decreased. By increasing of basicity, the concentration of hydroxide ions is increased. The pH and pOH scale is of the great theoretical and practical importance in analytical chemistry, since it can be used to calculate the concentration of hydrogen and hydroxide in solutions, their effect on equilibrium states in solutions of substances, and to carry out qualitative and quantitative analytical reactions. Now about the calculation of pH of acids and bases. Calculation of pH of medium is one of the most frequent calculation operations carried out by an analytical chemist. Calculations is carried out to determine the concentration for the analysis, the choice of indicators, to construct titration curves, the conditions of precipitation, methods for calculating the pH of medium in aqueous solutions, differ depending on the strain of acids and bases. The pH of strong acid depends on the concentration of acid, and the pH of strong base depends on the concentration of the bases. The pH of weak acid mathematically depends on the concentration of acids and the acidity constant, and the pH of the weak base mathematically depends on the concentration and on the basicity constant of bases. Calculation of pH in strong acid solution. For example, for calculation of pH, hydrogen chloride, nitric acid, sulfuric acid, and other strong acids. In solution of strong acids, the acid is completely ionized and the amount of the formed hydroxonium ions or simplified hydrogen ions is practically equal to the number of dissolved acid molecules. Consequently, the concentration of hydrogen ions in such solutions is equal to the concentration of the acid in unit of molarity. In this case, the concentration of, as we say, the concentration of hydrogen ions equal to the concentration of acids, and pH is equal to inverse logarithm of concentration of hydrogen ions, and as the concentration of the hydrogen ions equal to the concentration of acids, so pH equal to the inverse logarithm of the concentration of acids. For example, calculate pH and pOH in 0.05 mole of hydrogen chloride solution. As the concentration of hydrogen ions is equal to the concentration of acid, so pH equal inverse logarithm of the concentration of acid. From this calculation, it is found that it's equal to 1.3. And knowing pH, it is possible to find pOH. pOH equal 14 minus pH is equal 12.7. It is possible to find pH and pOH by the ionic product of water, knowing the constant of autoprotolysis, that it's equal to the product of the concentrations of hydrogen and hydroxide ions, and they are equal to the 10 to the minus 14 power. We found a concentration of the hydroxide ions, it's equal to the ratio of the constant of autoprotolysis to the concentration of hydrogen, and we find pOH, and instead of this formula we write the values of constant after protolysis. It's a constant 10 to the minus 14 power divided to the concentration of acid, and it's equal 0.05. From this we find concentration of hydroxide ion, and knowing this we find pOH, and it's equal 12.7. So it is possible to find pH and pOH values by two ways. The first equation is true for acid solutions with a concentration not lower than 10 to the 6 power mole liter. In more dilute solutions, it loses its meaning since, for example, for an acid solution with a molarity of 10 to the minus 8 mole liter, the pH calculated using this equation would be 8. By the way, pH equal inverse logarithm 10 minus 8, so it is 8. Therefore, when calculated the pH of the dilute acid solutions, the process of water autoprotolysis is taken into account, and the concentration of hydrogen ions is taken equal to the sum of the ion concentrations obtained during acid ionization and released during water autoprotolysis. The concentration of hydrogen ions formed during the ionization of the acid hydrogen ion is equal to the concentration of acid, The concentration of hydrogen ions formed during the autoprotolysis of water is equal to the concentration of hydroxide ions, and the general concentration of the hydrogen equal to the concentration of acid plus concentration of hydroxide ions, and it is known that concentration of hydroxide ions equal to the ratio of constant autoprotolysis divide concentration of hydrogen, and if we put instead of hydroxide ion the values of OH, concentration OH, it is forms the form a new formula for concentration of hydrogen ions. After transformations from the second new formula, we obtain a quadratic equation and its solution, and we found from this concentration of hydrogen using this formula. For example, the concentration of hydrogen ions in the concentration 10 to the 8 minus 8 power molarity of hydrogen chloride, and instead of the first this formula we write the values of the calculation. Knowing this, it is easy to find concentration of the hydrogen ion. After this we find the pH, it is equal 6.98, and knowing pH we find POH. 14 minus values of pH, it is equal 7.2. Calculation of pH in strong base solution. Calculation of the pH of, for example, sodium hydroxide or potassium hydroxide solutions. In the solutions of strong bases, the concentration of hydroxide ions due to the complete ionization of the base in water is equal to the concentration of the base, and is found from the equation. In this case, concentration of the hydroxide groups equal to the concentration of base, and concentration of hydroxonium ion equal to the ratio of constant autoprotolysis to the concentration of hydroxide groups, and pH value, it is known 14 minus POH. In dilute solutions of strong bases, the values of the concentration of the base is less than 10 to the minus 8 power moliliter. Similarly, as in the case of the dilute solution of strong acids, the concentration of hydroxide ions is equal to the concentration of hydroxide ion equal to the concentration of base plus the ratio of constant autoprotolysis to the concentration of hydroxide ion, and we find the concentration of hydroxide ion. And there is an example for this. For example, calculation of pH and POH for a strong sodium hydroxide solution. If there is a concentration of the strong bases, it is equal to 0.1 mole liter. It means the concentration of hydroxide ions equal to the concentration of this strong base equal 0.1 mole liter, or 10 to the minus 1 power. And we find POH, it's equal inverse logarithm of the concentration of the base, and it's equal 1. pH, we find pH, knowing POH, it's 13, and using the ionic product of water, it is possible to find the same values. concentration of hydrogen ion is equal to 10 to the minus 13 power, pH equal to the inverse logarithm of the concentration of hydrogen, and it's equal 13, and the concentration of hydrogen ions is equal to the 10 to the minus 13 power. There is a table with the pH of the acids and bases, strong acids and weak acids, also the salts. There is also weak and strong bases, value, pH value of these. For example, there is a noun, we find the constant pH value for the strong base, sodium hydroxide, it's 13, and it is seen from the table, it's 13. And there is also the different values, pH values for the different substances. For example, for 1 molarity concentration of sodium hydroxide, pH value is 14. For ammonium, for example, it's 12. For milk, it's between 6 and 7, and others. For example, calculate the pH of the 0.001 normality concentration of sodium hydroxide solution. Sodium hydroxide, it's strong electrolyte. Dissociation in an aqueous solution occurs according to the following scheme. Sodium hydroxide decomposite on dissociated on positively sodium ion and negatively charged hydroxide ion, and the degree of dissociation in the dilute solution can be taken equal to 1. The concentration of hydroxide ions in mol/liter in the solution is equal to 10 to the minus 3, because the concentration of the alkali is 0.001 normality, and so the concentration of hydroxide group equal to the concentration of the base. And knowing this, it is possible to find the concentration of hydrogen. It's equal to the 10 to the minus 11 power, and pH equal to the inverse logarithm of concentration of hydrogen, and it's equal to the 11. The next calculation of the pH of weak acids, for example, acetic acid, formic acid, hydrogen cyanide. In this case, in solutions of weak acids, it must be taken into account that not all acid molecules decompose into ions. For one protic acids, the concentration of hydrogen ions is equal to the concentration of the formed acid anion, and the remainder of non-ionized acid molecules is equal to the total acid concentration minus the concentration of hydrogen ions. In this case, non-ionized acid molecule, weak acid molecule, equal to the total acid concentration minus to the concentration of hydrogen ions. From the acidity constant equation, after substitutions, we get a calculation of equilibrium constant, and they are all values of equal to the 0, and from this we find concentration of hydrogen. It's a third formula, and from this formula, if the acid is weakly ionized, the degree of dissociation less than 0.03, then the denominator of equation 3 can be taken equal to concentration of acid, and then we find the constant of acidity. Hence the concentration of the hydrogen equal to the root is equal constant of acidity, product of constant of acidity and concentration of the acid under the root, and pH equal to the following formula. Since acetic acid weakly dissociates into ions, the concentration of hydrogen in the equation in the denominator neglects, and find concentration of the acid equal concentration of acid and product of the constant of acidity multiplied concentration of acid in the root. For example, it is necessary to find pH of the 0.5 mol/liter concentration of weak acid solution with a constant of acidity equal 1.8 multiplied 10 to the minus 5 power. Using this formula for calculation of the hydrogen concentration, we find that the concentration of hydrogen equals 3 multiplied 10 to the minus 3 power. And knowing the concentration of hydrogen, we find the pH, which is equal to the inverse logarithm of hydrogen. So inverse logarithm 3.3 multiplied 10 to the minus 3, and from this it's known that equal 2.52 or approximately 3. The fourth calculation of the pH in weak basis solution, for example for ammonium hydroxide, there is equation of the reaction of weak base with the water. In this case B, it's a weak base, BH positive, it's a conjugated acid, OH conjugated base, and decomposition reaction of the weak base solution. From this we find concentration of the B, concentration of weak base, it's equal concentration of the general concentration of base minus concentration of hydroxide group, and we find the constant of equilibrium, simplified form of basicity constant, and hence concentration of hydroxide ions equal to the constant of basicity multiplied to the concentration of base in the root, and we find POH and pH. For example, calculation of pH of 0.1 mol/liter concentration hydrogen chloride, ammonium hydroxide, and knowing the formula above, we find the concentration hydrogen or hydroxide group. It is found from the known formula, and we find 1.34 multiplied 10 to the minus 3, and we find POH, it's equal to the inverse logarithm of the concentration OH group, and instead of the OH concentration of OH, we write the value 1.34 multiplied 10 to the minus 3, and it's found 2.89. Knowing POH, it's possible to find pH. It's equal from the calculation 11.11. Fifth, it's polyprotic acids are ionized in the several stages. So when calculating pH in solutions of polyprotic acids, the concentration of hydrogen ions formed during ionization through the second and subsequent stages is neglected. Taking polyprotic acid as one protic acid, the calculation of pH in solutions of such acids is carried out according to formulas that take into account the first acidity constant, and the first acidity constant we denoted as acidity constant Ka prime, and we find pH. For example, for 0.1 normality concentration polyprotic acid orthophosphoric acid, the approximate pH value is calculated with the following way, and there is find the acidity constant for orthophosphoric acid, then it's find concentration of hydrogen ion, and at last find pH, which is equal 1.58. In acidic mixture, the concentration of hydrogen ions depends on the type of the acid. In a mixture of strong and weak acids, the process of ionization of a weak acid is separated by a strong acid due to the appearance of an excess of hydrogen ions during its complete ionization. Therefore, in an approximate calculation of pH, in such solutions, the presence of weak acid with index of constant more than dissociation constant more than 4 is neglected, and the formulas used for strong acids are used. Concentration of hydrogen ions equal to the concentration of the acid, and pH equal to the inverse logarithm of acid's concentration. For example, in a solution contains of 0.1 mole of hydrochloric acid, and there is a mixture also acetic acid, the ionization of acetic acid is 1.8 multiplied 10 to the minus 5 power is separated, and the equilibrium is shifts towards the formation of weak acid, and the concentration of hydrogen equal to the concentration of acid, and it's equal 0.1, and the constant of acidity of acetic acid is find, and from this equation we find 1.8 multiplied 10 to the minus 8. And the last one, in a mixture of two weak acids with the general formula HA and HA2, the concentration of hydrogen ions depends on the processes of ionization of both acids and water, and can be calculated using a system of equations including acid ionization constant and balance equations. When diluting solutions of weak acids and bases to a concentration of 10 to the minus 5 power moliliter and below, their complete ionization occurs. Therefore, in dilute solutions of weak acids and bases, which with the concentration of the range of 10 to the minus 5, 10 to the minus 7 power moliliter, it's advisable to use the formulas derived for solutions of strong acids and bases for calculating pH. It was the last information of our lecture. Thanks for attention.